you can start.
All right, hi everyone. So Kadir is going to talk about complex analytic sets and Chow's theorem. And I think he's been a model student for DRP this season, and it has been a joy to discuss mathematics with him for the last few weeks. Without further ado, let me leave it to Kadir, and good luck.
Yeah, hello everyone. First of all, I want to thank my mentor for his patience, wisdom, and this time. And today I'm going to talk about complex analytic sets and Chow's theorem. Yeah, let's start with the outline. I'm going to define analytic sets, then I'm going to give some examples and non-examples of analytic set, then I'm going to talk about fundamental concepts for analytic sets, like regularity, singularity, and so on and so forth. And then we will see some propositions for which we will use for the proof of Chow's theorem, and this will be our main result. Okay, let's start with the definition of an analytic set. What is a complex analytic set? They are actually locally look like the zero locus of finitely many holomorphic functions. But we are considering what do we mean by zero locus? We are taking points from omega, and we are find a neighborhood of that points, and then we are looking for this intersection, and we are representing this intersection using these zeros of this finitely many holomorphic functions. If we change this part of the definition, if we take a instead of omega, then we get a more generalized definition, and which is a definition of analytic set. Analytics subsets, this thing is called analytic subset. Analytic subsets are closed, and analytics sets are locally closed. Yeah. Okay, we have some examples. First of all is a classical one, carton umbrella. We have yeah, this is the picture of it. We have a plane and we have a line. We are considering their union, and they have an intersection point, say 0. By the way, line is not on the plane, and this is an analytic set. Why? Because we can pick a point on the plane, and it is locally we can locally define it by using the equation of plane to zero locus of a holomorphic function, and we can repeat same argument for line. What can we say about intersection? Take point 0 and consider we need to find a actually, if we go back to the definition, we see that we need to find a neighborhood. So we can choose two neighborhoods, lots of many neighborhoods. In this example, maybe you can select a neighborhood on this plane or on this line. It doesn't matter. It's corrects the definition. Okay. Yeah. This point, this intersection point, is something that's called singular point. We will explain it later. And our second example is the semi-cubic parabola. The set is defined like this, and if you subtract that one tree from both sides, you get a polynomial on the left-hand side, and this is actually the polynomial is of course a holomorphic function in C2. Then it is it's obviously from definition an analytic set, but this is a particular one because this is a zero locus of a polynomial. So such sets called affine algebraic sets. Affine algebraic sets are the zero set of polynomial functions in CR. Complex algebraic sets, of course, or complex affine algebraic sets. And third one is a non-example. We are taking set A. This is a set of 1 over n's, and we are adding 0 to this set. And why this is an example? If, take point 0, take a neighborhood around it, and let's assume that we can represent it as a zero locus of finitely many holomorphic functions. Since this is an accumulation point of this set, if you by identity theorem, these holomorphic functions must be identically zero because it's an accumulation point, and you are taking a locus around it, and they are zero at that point. Yeah, they are zero at that locus. So this cannot be an analytic set, but if we remove zero. If we remove zero, we get an analytic set. Because we can represent these points by using polynomials. Let's say take 1 over m and take polynomial z minus 1 over m, then locally you can represent that point by using that polynomial, which is holomorphic. And if you have a couple of points, maybe 1 over n and 1 over m, you can take polynomial z minus 1 over m multiplied by z minus 1 over m. So it is again an analytic set, but it is not an analytic subset. Why? Because consider point 0 is a troubling point, and we remove that. But if we go back to the definition, we see that this is true for when we are considering the definition of analytic subset. This is true for all points in omega or our ambient space. So since our ambient space is C and 0 is still in C, this is not an analytic subset, but it is an analytic set when we remove 0. And if we add 0, it is not an analytic set or analytic subset. So these are examples and non-example. Okay, now definitions. Okay, we want to understand this analytic sets, and we want to measure their behavior. And how can we measure their behavior? By using dimension concept. But we want to define a dimension concept, but something is there is something troubling here, because if we check this definition, we see that the number of defining functions is not fixed, and also their rank is not also fixed. If you know the complex embedded manifold definition, they are fixed in that definition, but in this case, they are not fixed. So since they are not fixed, if we try to define a dimension concept, we actually don't have a fixed dimension concept. So distribution of dimension intuitively not constant. So in this case, we need to do something different. It is a harder problem to define dimension, but we need dimension. So we need to define another thing. But since the definition of analytic set is not that different from the definition of a complex embedded manifold, we can consider the points which are locally look like submanifolds, complex submanifolds. These points are called regular points, and set of these points are called reg A, this guy. And we can define, of course, a dimension concept around them because they are complex submanifolds. And let's denote this dimension 1 by dim AA. Okay, but we can also consider points which are not locally look like submanifolds, complex submanifolds, which points are called singular points, and these it is formally defined by the complement of these regular points in A, and we denote this set by sing A. We also have we want to collect all troubling points, all troublesome points into a set. This set is called singular. It of course contains sing A, but it also contains low dimensional points. We didn't define a dimension concept yet, but soon we will. And these points are points which have smaller dimension than dimension of A, which will prove in defining next slide. Okay, yeah, definition. So we have regular points. By the way, the regular points are dense. There is a theorem. Regular points are dense in A. So actually, general behavior of an analytic set is not so different than the behavior of a complex manifold, locally speaking. And since they are dense, by using them, we can define the dimension concept for analytic sets. So let's take a point from A, and let's take a sequence which converges to A, then we can, by the way, by this, I meant sequence of dimensions of the points around that A. So we are taking that sequences and we are taking the supremum of the dimensions. So I mean the lim sup of the dimensions around A, and we are defining the dimension AA is the lim sup of dimension. Actually, I can explain on an example. If we consider Cartan umbrella, what is the dimension of intersection? The points on the line, the dimension of points on the line has dimension 1, of course, and this guy's dimension 2, which if we consider the intersection, dimension is 2 because we are taking the lim sup. So yeah. Then easy part, define the dimension of A. We define the dimension of points of A, so we are taking their maximum. How can we take the maximum of that points? Because the dimension of A cannot exceed the dimension of ambient space omega, so we have finite many choice, so we can use we can take the maximum. Okay. Now we are going to talk about a proposition about regularity in PM. What is PM? You know, PM is complex projective space, and it's defined as the you are taking Cn plus 1 star. Star means you are removing 0. Then you are considering equivalence class, and equivalence relation is the being on the same line. And there is of course a canonical projection for that. The canonical projection for Cn plus 1 star to equivalence classes, which we denoted by pi. So proposition says you have an analytic set in Pn and you are considering its pre-image. And it says numerically it is an analytic subset. And then if it is an analytic subset, it has regular points, singular points, and singular roots. So if you project it again, then you get the regular points of A, singular points of A, singular loops of A, because you are taking pre-image and then taking image of them. So naturally, it gives this. And then there's another important thing. The dimension of A tilde in any point of it is higher by 1 than dimension of A. Why? Because when you take the canonical projection, you are reducing dimension by 1, but we are taking pre-image, then we are the A tilde dimension is higher by 1. We are not going to prove this result. It has a really technical and beautiful proof. It uses rank theorem, etc. You can check it from Chika's book. Okay, let's continue. There's another beautiful result, which is called Riemann-Stein theorem. So we are taking a pure p-dimensional analytic subset in omega minus S. S is an analytic subset of this complex manifold. And we want to extend the analyticity of A to all omega. How can we do that? If S is small enough, we can do that. And we measure the smallness of S by using dimension concept. So dimension of S is less than P, we can do that. And then our analytic set A is also an analytic subset in omega. This is the statement of Riemann-Stein theorem. We also not going to prove it. But if the proof uses actually Hausdorff dimensions, etc., you can check the proof again from the book. We are actually using this proposition as a machinery for Chow's theorem, which will be our main result. Okay, we are taking a family of arbitrary family of holomorphic functions, which are holomorphic on omega, and we are considering their zero loops. So they are not they might be infinitely many of them. So we don't know anything about their zero locus is analytic or not. We don't know anything about their zero locus. But this proposition says it is analytic. So since it is analytic, we can see it as a zero set of finitely many holomorphic functions from the definition. Then these are the functions. Actually, if you check the proof from Chicago's book, you can see that they are infinitely near combinations of these f alphas, and you are choosing their coefficients CKs for the infinitely near combination being uniformly convergent. Okay, and we are here. We are going to talk about affine projective varieties. So we defined an affine algebraic set. Projective algebraic set has a similar definition. It has a similar definition. You are considering homogeneous polynomials instead of arbitrary polynomials, and your zero locus in actually not in CN this time in PN, and this gives the definition of projective affine variety. There is a correspondence between affine varieties and projective affine varieties using the projectivization. But before time, because of the time constraints, we skip this part. Okay, now let's check our main results. By the way, every affine algebraic set can be represented as the intersection of some algebraic sets, and any projective algebraic set is locally affine. Then, in particular, it is an analytic subset in Pn. But is converse true? Chow's theorem says yes. Yes. Okay, let's prove it. Let A be a purely p-dimensional analytic subset in Pn, and let pi be the canonical projection. Then the main idea of proof is we are going upstairs first using this pre-image and then pre-image theorem, and then we are doing some stuff, but we are using some propositions, and then we are going back with using again projection and get A, and then we are gonna we will see that it is a projective algebraic set. So first we use pi minus 1a, and it is an we know that it's an analytic subset because we set that in proposition for the regularity in Pn proposition. And we know that it is dimension is higher by 1 than dimension of original 1. So it is pure p+1 dimensional analytic subset in Cn plus 1 star. So star means we don't have 0. We can use the Riemann-Stein theorem. Actually, this part is wrong. I need to correct that part. Yeah, we are in Cn plus, and we don't have 0. This is the point 0, this function point. Okay, and we have pi minus 1a. This is an analytic subset in Cn plus 1, and theorem says if the dimension of 0 is smaller than p plus 1, it is of course. We can say that this is closure of this set is an analytic subset in Cn plus 1. And if you take this closure of it, if it is not containing 0, then p minus 1 this guy is an analytic subset of Cn plus 1, but if it is containing 0, you need to add the 0 to the closure. So you are, but it is, since it is closed in Cn plus 1 star, this is equal to p minus 1a, and this is p minus 1. Yeah, if it is containing 0, then the closure equals to this. So in any case, you can, in this case, this is an analytic subset, but since just 0 can be seen as an analytic subset because it is complex manifold, 0-dimensional complex manifold. In that case, this is also an analytic subset. So combine this, the end result would be this set, pi minus 1a union 0 is an analytic subset. Remove that part, this is the one, as I explained. Is a sentence true, sentence wrong. Okay, is an analytic subset in Cn plus 1. As there exists, but by using the definition, we can find GIs, which are holomorphically represents the local of 0, and we can select our neighborhood above, because we can, if we have a neighborhood, we can shrink it into above. Evet, yes. Then, since these GJs are holomorphic, we can expand to a Taylor series. Then if we arrange the terms of Taylor series, we can get this holomorphic coefficients. Then if you have a z in a theta intersect u, then tz is also in this set because of the comp property. And why this comp property is true? Because we are considering the pre-image and they are in the same equivalence classes. They are on the same line. And we also consider as an extra condition the magnitude of t, the absolute value of t is less than 1. Why we are adding this? Because we want to use this tiny series representation for tz. Then if it is identically 0, this means it is 0 for all t's, then it implies that coefficients are 0. And we want to show the converse, and we are trying to actually replace these GJs by homogeneous polynomials, these coefficients. And let's prove the converse one. Conversely, if you have these coefficients identically 0, then it is in this intersection, and then these GJs are 0, then they are in that intersection. Thus, the intersection of set of common this intersection is the set of common zeros of the quantum system of polynomials, these homogeneous guys. So we replace GJs by these homogeneous coefficients, but we have a problem. We have infinitely many coefficients, so we need to use the number of defining functions theorem. But if we use that, we need to that theorem works for a complex ambient space. So so we need to shrink our neighborhood a little bit more. Then we can use the theorem and we can obtain the finite main defining functions, and we will denote them by pi's. Since a tilde is a comp, we can they are locally defining it. They are defining it in that local. But since a tilde is a comp, we can extend this definingness to all a tilde. So they will define all of a tilde. So let's project back and get A. So this is a projective algebraic set, and this concludes the proof. Time over. No, it's over. Yeah, thank you for your time. These are my references.